Hello, my name is Michelle Romero, and we are going to talk about entropy production and irreversibilities. My group is made up of
Sebastián Ramos Loboa.
Juan Moreno.
Rafael Jiménez.
the Calvin plaque statement. The Calvin plaque statement of the second law of the thermodynamics says it is impossible to construction a heat engine that operates a cycle and converts aldehyde into absorber from a single thermal reserve into work. In simple terms, every heat engine must reject heat to colder reservoir. In simple terms, every heat engine must reject heat to colder reservoir. Explanation. A real heat engine is about heat QH from a hot reservoir, produce work W and must release heat QS to a cold reservoir. W is the same QH minus QS. Clausius statement. The Clausius statement of the second law says it is impossible for heat to flow from a colder body to other body without external work being supplied, meaning heat does not flow spontaneously from a cold to hot. Work is required from the process, refrigeration and heat pumps. Connection with Calvin plaque. Both statements are equivalent, violating one word automatically violate the other. Reversible and irreversible process. Reversible processes are ideally processes that can be reversed without leaving any change in the system of reactions. Key characteristics. They occur extremely slowly, QC is static, no friction is present, no fine temperature difference, no energy dissipation. They produce zero entropy. Examples: quasi-static reduction expansion, with transfers with infinitesimal temperature difference. Irreversible process. Irreversible processes are real natural processes that can be reversible without leaving effects of the system of surroundings. Source of irreversibility. Friction, finite temporary gradients, free expansion, mixing of substances, chemical strictness, electric resistance that produce positive entropy.
Irreversibility. Irreversibilities are real effects that cause a process to deviate from the ideal reversibility behavior. They always generate entropy production and reduce system efficiency. The main source irreversibility are friction. Mechanical friction between moving parts converts useful work into heat, causing energy dissipation and entropy production. Examples: piston turbines, compressors, and bearings. Mixing of substances. When different gases or fluids mix spontaneously, the resources increases and entropy rise. This process cannot be reversed without external work. Finite temperature heat transfer. Heat transfers that occurs with infinite temperature difference. For example, hot dog cold rapidly is always irreversible. Reversible heat transfer cannot only occur with an infinitesimal temperature difference. Sources of irreversibility. Electrical resistance. When an electric current flows through an resistor, energy converted into heat, Joule 18, producing entropy. Inelastic deformation and turbulence. An non-ideal fluid vapor, such as turbulence or viscosity effects, leads to entropy generation, as we can see in the images. What entropy is a relationship with heat and temperature. What is entropy? Entropy is thermodynamic property that measures the degree of resources, energy dispersion of irreversibility of a system. It increases when energy becomes more spread and the less available to the usual work. Relationship with heat and temperature. For unreversible process, the changes in entropy is defined as we can see in the images. Heat added to the system increases entropy, especially at low temperatures. Heat removed decreases entropy. For finite process, as we can see in the images, how entropy is calculated. Entropy can be calculated depending on the type of the process and the information available. These are the main cause. 1. For an reversible process, the definition of entropy is what we can see in the images. And for an infinity reversible process, as we can see in the images. 2. For an ideal gas, constant specific heat changes in entropy with temperature and volume, as we can see in the images. And changes in entropy with temperature and pressure, as we can see in the images. And 3. For an ideal gas using absolute entropy, as we can see in the images. How entropy is calculated. 3. For an ideal gas using absolute entropy, as shown in the tables, and as we can see in the images, where SOT equal absolute entropy from thermodynamic tables, R equal constant gas. 4. For adiabatic irreversible process, even if Q equal 0, and as we can see in the images, entropy still increase due to irreversibilities, friction, mixing, finite heat transfer, etc. Entropy generation. This is important for your topic, as we can see in the images. Reversible process, S gene equals 0. irreversible process is G greater than 0.
Example, free expansion of a gas, classical case of total irreversibility. Free expansion or expansion into vacuum is a process in which a gas expands without any external resistance. It is a perfect example of entropy production. System description. A thermally insulated cylinder is divided into two compartments. Left side, 1 mole of ideal gas at. Temperature 1 is equal 300 Kelvin. Pressure 1 is equal 1 atmosphere. Volume 1 is equal 24.7 liters. Right side, vacuum, pressure is equal 0. When the barrier is removed, the gas expands instantly. Process free expansion characteristics. No heat transfer equals 0. No work done, work equals 0. For an ideal gas, delta U equals 0 when temperature 2 equals temperature 1. The gas expands to the total volume. Volume 2 equal 2 by volume 1 equal 49.4 liters. Entropy change calculation for an ideal gas. Delta S equal N by R by natural logarithm by volume 2 on volume 1. Example, free expansion of a gas, classical case of total irreversibility. Entropy change calculation, substituting values. Delta S equal 1 by 8.314 by natural logarithm by 2 equal 5.76 joules on Kelvin. Entropy increases, entropy generation is positive. S gen equal 5.76 joules on Kelvin. Why is the process irreversible? Because the expansion occurs with no external force opposing expansion. Extremely fast, uncontrolled process. It is impossible to return to the original state without expending work. Thus, S gen greater than 0. 2. Effect on process efficiency. Irreversibility such as friction, mixing, free expansion, and heat transfer with large temperature difference always reduce efficiency. Efficiency and entropy. Final thermal efficiency Carnot. N Carnot equal 1 less TL on TH. With irreversibilities, N real equal N Carnot. Loss due to irreversibility. Effect on free expansion on efficiency. In the free expansion, no useful work is produced. Work equals 0. Entropy increase. S gen greater than 0. This means the process produces no useful energy, moves the system away from the ideal reversibility limit. What's energy that could otherwise produce work? Process efficiency equal 0. It is the less efficient process possible. Effect of gas mixing on efficiency. Gas mixing increases entropy, produce irreversible loss. External work will be required to separate the gas again. Loss of a value useful work. Lost work. The work loss equal temperature 0 by S gen. Example at temperature 0 equal 300 Kelvin. Work loss equal 300 by 11.53 equal 3,459 joules. Every joule loss reduces the actual efficiency of any device or cycle.
With the first law. The joint evaluation with the first law of thermodynamics consists of simultaneously analyzing the substance energy balance, first law, and the entropy generation associated with the process irreversibility, second law, in order to determine not only how much energy is conserved, but also how much of it remains available to perform work. This evaluation integrates the following concepts. 1. Relationships by the Kelvin, Planck's, and Clausius statements. The statements of the second law indicates the natural limitations on the use of energy. Not all heat can be converted into work. Kelvin, Planck. Heat does not spontaneously flow from cold to hot. Clausius. Combining this with the first law, we understand that although total energy is conserved, not all of it is usable due to these limitations. 2. Reversible and irreversible process. Reversible does not generate entropy, maximum efficiency. Irreversible generates entropy, loss of capacity to produce work. The combined evaluation allows us to identify how much of the energy calculated with the first law is degraded in a real process due to irreversibility. 3. Source of irreversibility. Friction, mixing, heat transfer with temperature difference, and other sources produce an increase in entropy. The first law does not distinguish between these laws, but the second law does reveal its impact through the entropy generated. With both together, it is possible to quantify how much useful energy is destroyed. 4. Entropy, relationship with heat and temperature. Entropy connects thermal energy with the quality of that energy. While the first law quantifies energy, entropy quantifies the loss of availability associated with its dispersion.